pressure.
Low pressure. Remember? And then the next thing to remember is, since we can't change atmospheric pressure, that means that if we want air to come in or go out, we have to change what's going on inside of our lungs. We have to change the pressure in there, because we can't change this. So, to change pressure, actually let's do this. To change pressure, we have to change volume, and I'll explain that in just a second. To change volume, we have to make muscles of ventilation either contract or relax. And these are skeletal muscles. And we'll go over what those are in a second too. Okay. So let's think about this for a minute. Okay, so Boyle's law says that as you increase pressure, volume goes down and vice versa. So volume and pressure are inversely related. So as pressure goes down, actually let me word it this way. It'll make a little more sense when we go over it. As you increase volume, pressure goes down, and as you decrease volume, pressure goes up. So let's think about this for a minute, okay? So let's say that I had a certain amount of air, and the amount of air is not going to change in this example, okay? We're thinking about this right now. So I have a certain amount of air, and I have it in a container this big, okay? And the air molecules that are in there are bouncing against the wall, and that sets up pressure. Okay, so this volume sets up a certain amount of pressure, okay? Same amount of air, but now if I make that volume go really small, now those molecules are really bouncing against the wall and pressure goes up. So as the volume goes down, pressure goes up.
Oh, okay, because you're compressing it.
Because I'm compressing it, right? Or if I take that same amount of air, but now I put it in this much space, now they're just like boom, 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 and pressure goes down. So volume's bigger, pressure's down. So volume and pressure inversely related. Okay? Alright. So air is only going to move if I get pressure differences between what's in my lungs and out here. And I can make the pressure change by making the volume in my lungs change. Okay? And I can make the volume in my lungs change by making muscles contract or relax. Okay, now what muscles? Muscles of ventilation. You have your respiratory diaphragm, and again, these are all skeletal muscles. Okay, so respiratory diaphragm is a big dome-shaped muscle at the base of the lungs. Right here. Okay. And when it's relaxed, it's domed up like that. And then we have external intercostals. And these are attached to the ribs. And then we also have internal intercostals, and they're also attached to the ribs. Alright, so I'm gonna say for inspiration, about is if I want air to come in, I have to make the pressure in my lungs lower than the pressure out here. Because then air will move from high pressure to lower pressure, okay? So I always think about that first. So for inspiration, what I need is I need the pressure of my thoracic cavity, which is where my lungs are, in the thoracic cavity. Or I'll just put thoracic pressure. I need my thoracic pressure, so we'll say pressure in the lungs, to be lower than atmospheric pressure. Pressure up here, okay? And whatever we do to the lungs, okay, the same thing's gonna happen to the alveoli that are inside the lungs. So if we make the lungs get bigger, then the little alveoli that are inside the lungs will pop open. And we'll kind of look at how that works when we're done with this. Okay, so for right now, just go with it, and then we'll explain that later, okay? And if we make the volume of the lungs get smaller, then the little alveoli that are inside, they get smaller too, okay? So we can replace this with alveolar pressure needs to be less than atmospheric pressure, because that's really where the air is in those alveoli, okay? All right, so this is what we need, okay? So then the question is, how do we make the alveolar pressure get lower? The way we make alveolar pressure get lower is by making thoracic pressure get lower, or lung pressure get lower. And the way we do that is by making thoracic volume and alveolar volume get bigger, okay? So then the question is, how do we make them get bigger? And we're gonna do that by making muscles contract. Okay, so what we're gonna see happen first is, so I always stop, before I start doing this, I always stop and say, what do I need to have happen? Okay, and actually, let's just write this. I will say, by making the volume in the alveoli increase. Okay. So, first thing that we're gonna see is we're gonna see an increase in action potential frequency traveling along somatic motor neurons going to the respiratory diaphragm and the external intercostals. And I'm going to abbreviate that from here on out as EI. Okay. So remember, these are skeletal muscles, so we don't use sympathetic and parasympathetic. That's for cardiac muscle and smooth muscle. This is what we did last quarter. So just making the skeletal muscle, if you make action potentials travel faster, more acetylcholine's released, muscle contracts. If you want those muscles to relax, you just slow down the action potential frequency, less acetylcholine, muscle relaxes. Okay. All right, so for these guys, if we look at our lungs, okay, so we're gonna put left lung, right lung, and at rest, the diaphragm domes up like this. Okay, so that's your respiratory diaphragm. And so as we increase the action potential frequency, the diaphragm's gonna contract, and when it contracts, it flattens out. Okay, so we'll put this here. We'll say contract. Contraction of diaphragm. When it contracts, it flattens like this. Now, when the diaphragm contracts, it flattens. And we're also going to have contraction of the external intercostals. Okay, so both sets of muscles are going to contract. When the diaphragm contracts, it flattens. So flattens. Here it's okay. And when these guys, actually let's put this, we'll say the diaphragm flattens. And when and the external intercostals contract, they're gonna elevate the ribs and sternum. So the ribs and sternum come up and the diaphragm flattens.
Is it like pulling onto? the
Yeah, it
diaphragm?
pulls the
Okay.
ribs up. So basically, it causes these guys, when they contract, it pulls this stuff up. So they're just, the muscles just go from here to here, here to here, here to here, here to here, here to here. And when it contracts, it just pulls it all up.
Oh,
Okay. So, when your ribs and sternum come up, obviously I'm exaggerating how much it comes up, and your diaphragm flattens, that gives the lungs more space,
Mhm.
right? There's the thoracic cavity is bigger now. And we'll talk about this in a minute, but because if you look around the lungs, there's lots of elastin, that springy protein, which means it can expand and recoil a certain amount. Okay, so if you give the lungs more space, and I think the misconception is the air comes in, it makes the lungs go, no air has moved yet, okay? It's the same amount of air that was in there before, same amount of air. It's just that because we give the lungs more space, because of all that connective tissue, that elastin, they'll just expand, okay? So the lungs get bigger. So this right here is causing the thoracic volume to increase. These muscles contracting, the diaphragm and the external intercostals, allows the lungs to get bigger, the volume of the lung gets bigger. And the little alveoli inside the lungs, they pop open. And we'll see how that works in a minute. But this causes an increase in the alveolar volume. Now remember, the same amount of air was in there here as is in here now. And as that alveolar volume gets bigger with the same air in there, that causes alveolar pressure to start dropping. Just like we talked about over here. So, as soon as, we'll call this 2, as soon as the alveolar pressure becomes lower, because it's dropping, becomes lower than atmospheric pressure, air starts moving in. Inspiration. Now, think about it like this. As that air starts moving into the alveoli, as we start putting more and more air in there, what starts to happen to the pressure in the alveoli now? It increases, right? So as air's moving in, the pressure in the alveoli is rising, 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 rising. So then, as air moves into the alveoli, that causes alveolar pressure to rise. And as soon as alveolar pressure rises to and equals atmospheric pressure, air stops moving. Does that make sense?
Yeah.
Okay. So that's how you get air to come in. Okay. So now, for expiration, I do the same thing. I just stop and think, what do I need to have happen? For expiration, I need the pressure in my alveoli to become greater than atmospheric pressure, and then air will go out. Right now it's equal. Okay. So, and air's not moving in, so we can't change pressure that way. Okay. So, in order to get alveolar pressure to go up, we're going to do that by decreasing the alveolar volume. And we're going to get alveolar volume to get smaller by decreasing thoracic volume. And we're going to do that by making muscles relax. Okay. And we can also do some contraction, which we'll talk about in a minute. Okay. But mostly it's relaxing. So then what we're going to see here is we're going to see action potential frequency traveling along the same somatic motor neurons to the respiratory diaphragm and the external intercostals decreases. Okay, and that's just happening without us having to think about it. We could think about it, like I want to breathe faster, and we can make that action potential go faster or slower. But we don't have to think about it because you have pathways coming from your brainstem going out to those muscles that you don't have to think about. Okay? So as that starts to slow down, then these muscles start to relax. So these muscles will start to relax. Basically, if you're not stimulating them, they will relax. Okay? So for relaxation, we're gonna have, so here we've got left, right, okay, that's a contracted diaphragm. And so now for relaxation, the respiratory diaphragm is gonna dome back up. It's gonna go back to its original position, like that. And then the external intercostals, as they relax, they're going to allow the ribs and sternum to go back to resting position. So over here, when they're contracted, they're elevated, so now they're just going back to rest. Okay. And all of this is going to cause that's going to make the lungs get smaller because they have less space now.
Yeah.
Okay. So this, and again, they can expand and recoil, so they're going to recoil again because of all that elastin around them. And something else that we'll talk about in a minute. So the lungs will recoil as they have less space in the thoracic cavity. We'll see that. And as they recoil, that causes their volume to drop. And as their volume drops, the little alveoli that are inside, they get smaller too, because they have less room. And again, we'll look at that more in a second, but that causes alveolar volume to drop. And again, we have a certain amount of air in there at this point, and so as the volume gets smaller, that same amount of air is still in there, but now pressure is increasing. So this is all causing an increase in the alveolar pressure. Come over here, we'll say, as soon as alveolar pressure becomes greater than atmospheric pressure, air moves out. And as that air is moving out, the pressure in the alveoli drops. Okay, so this causes, as air moves out, pressure in the alveoli drops. And then we can say as soon as the alveolar pressure goes from this high state and drops down to and equals atmospheric pressure, the air stops moving. And then right about this time, you see the action potential frequency pop back up, and you do the whole thing all over again.
Whole cycle again.
Cycle goes over. So now we just have to, so this is how you just do it, just a quiet breathe out, breathe in, breathe out, breathe in. This is your just quiet tidal volume right here.
Mm-hmm.
So then we just want to think, okay, what if you wanted to do this? What if you wanted to go, how do you do a forced expiration? And to do a forced expiration, so expiration, you're still doing this stuff, but to do a forced expiration, you just think, I'm just making the air move faster,
Mm-hmm.
right? So the air is moving out faster. And you probably have more air moving out, but let's not even worry about that. Let's just say the air's moving out faster. So the way you make the air move out faster is by making your pressure differences. The difference in pressure occur, make the difference in pressure bigger. If you have a bigger change in pressure, the air just moves faster. It's like having a concentration difference that's greater. Diffusion happens faster. Same idea. So if we make that pressure difference bigger, then the air moves faster. So then you say, how do you make the pressure difference bigger? You do that by making your volume difference, the change in volume, bigger. So then the question is, how do you make the change in volume greater? How do you make that bigger? And we're going to do that by, so we're still going to do this. Okay, so we're going to do this, okay, but then we're going to add one extra thing to this, okay, and we're going to do two. We're going to, so we're going to relax these muscles, and we're going to contract, so actively stimulate the internal intercostals. Now, what the internal intercostals do, they also are attached to the ribs, and when they contract, they pull, they depress the ribs in the sternum real fast. So this actively, so this is passive, and this is all passive. Stop stimulating it, it just passively goes back to rest. Here we're going to actively stimulate, boom, it depresses real quick. So this is active depression of the ribs and sternum. And when you actively depress the ribs and sternum, you make that change in volume happen, boom, real quick, okay? And it's a bigger change in volume, because you're not just bringing it down to rest, you're pulling it like this. So the volume difference is greater, okay? So this all causes the volume difference to occur faster and be greater, which then causes the change in alveolar volume to be bigger and greater, and then that causes the pressure difference to be bigger, to be faster and greater, to be faster and greater. And that all takes us back to right here, okay? So the air just moves faster, okay? So it's the same thing, you just also make the internal intercostals contract. That's basically what you do. So then, we have to talk about a couple more things, and that is surfactant and how the alveoli can recoil versus expand, okay? Can I erase this stuff?
Can I take a picture?
Yeah, go ahead. If you understand that stuff, I won't go into it, but if you want me to follow up with that too, I will.
Question.
Yep.
So, like the normal, like the quiet inhalation and exhalation, that's the inhalation, the the pressure, you want the pressure to go up?
Where?
You want the pressure to go up in the alveoli, right?
To do what?
Oh, like
Inhale,
to
exhale.
inhale. To
To
inhale.
inhale, so remember pressure, air moves from high pressure to low pressure. So if you make the pressure in the alveoli greater than out here, then the air will come out.
Oh, yeah, so
If you want the air to come in, you gotta make the pressure in here lower,
Oh, so the pressure
right?
is
So the air comes from high, so the pressure is always the same up here, pretty much.
Okay.
So if you want air to come in, you have to make the pressure in here lower than it is here, and then the air will come in.
So if you want air to go out, then the pressure here is higher than the pressure.
Yes.
Okay.
Yeah.
So we said like the normal, so if the pressure is high, if the volume is low, right?
Right.
And then how about enforced expiration and like inhalation, like is the pressure is bigger, the volume is bigger too?
Yeah.
Okay.
Yeah.
Okay.
Yeah.
Alright.
Yeah.
Thank you.
Okay, I'm gonna erase this stuff. Erase over here. So then, let's look at this. So then, kind of going along with this, what I'll ask you is, how can the lungs expand and recoil but not collapse? And how can the alveoli expand and recoil but not collapse? Okay, those would be two things I'd ask. So let's write that up here. Let's do them separately, okay? So let's say, how do the lungs expand, which is basically increasing their volume, okay? And recoil, which is decreasing their volume, but not recoil so much that they collapse, okay? So for the lungs, the way that they can expand and recoil, so expand and recoil is because of what we said. They have a lot of elastin in the connective tissue around and within the lungs. And so really they're pretty springy, the lungs are. So now, how do we make sure they don't collapse? Okay, so they don't collapse because of what are called pleural pressures. Okay, so let's look at this. If we take the thoracic cavity, let's just look at one, because the other one will be exactly the same. So that's the hollow space where the lung sits. And let's put the lung in there, and let's make the lung blue. Okay. So let's say that doesn't matter, let's just say that's your right lung. Oops. Okay, now there is connective tissue that lines the cavity and lines the lung. Okay. So let's do this. So there's connective tissue that lines the lung. And it adheres right to the lung. There's no space in between the lung and this membrane here. And then it also lines the cavity as well. Okay. And that is called, this part here is called your parietal pleura. And then the part that lines the lung, just like around the heart, same idea, that's called your visceral pleura. And as the lung is expanding and recoiling, what you don't want is those two to touch one another. And I've made this separation really big, it's teeny, right, teeny tiny. But you don't want them touching. So there's a little bit of space in between these two. I made it real big, but there's space in between here. And that space is called the pleural cavity. And in that is a little bit of fluid is in there, okay? So that's your pleural fluid is in there. And you don't want too much fluid because then it would put too much pressure on your lungs and that could make it collapse. But essentially what this space is in here, it's a negative pressure. So this space in here is contained. It doesn't have access to the outside. It's completely contained. And what that space does, because that is a negative pressure in here, it essentially works like a vacuum and it pulls outward on the lung like this. And that's what keeps the lung from collapsing. And this is why if you get a gunshot wound or like a stabbing that breaks this, and then air rushes in there, all that air rushing in there is then going to make the lung collapse.
Because of pressure.
Because all that pressure in there, yeah. Where normally there's like a negative pressure pulling backwards, kind of like, you know, if your lung is here, then all of us would be around the edge, grabbing hold of it and pulling it backwards so it can't collapse.
Yeah.
But as soon as air gets in here, then it collapses. So that's how this works here, okay? So then if we think about the alveoli, so then we say, how do the alveoli expand and recoil, but not collapse? So again, expansion is the volume increases, recoil is the volume decreases, but not recoil so much it collapses. Now we've got to think about the alveoli. Okay, so the alveoli, really fragile little structures, and they aren't much more than just a layer of cells. So I'm just going to put some cells here. Most of these cells are just simple squamous epithelial cells. There's some other cells embedded in here, but it's really just a single cell layer thick. So there's no smooth muscle in the wall, there's no connective tissue really. That's pretty much what it is, okay? And inside of here, you would have obviously air in here, and then a little bit of water in there. So they're not bags of water, but there's a few water molecules in here. Okay, so there's some water in here. So I'll put a water here, let's put a water here, let's put one here, let's put one over here. Or there'd be more than 4 molecules, but not a lot, right? So then, because this is so fragile, because it's so small and just a single cell layer thick, we have to start thinking about how water interacts, okay? So when you look at water, and I don't know how much of this you remember from bio. You should have learned this in bio, but I'm sure that's been a while. When you look at water, this is how it sits. All right, so H2O, okay? And each of these lines is a covalent bond, which just means you've got an electron from oxygen, an electron from hydrogen, and they orbit oxygen and hydrogen, oxygen and hydrogen. And the same thing for this line. You have a different electron from oxygen, an electron from hydrogen, and they orbit oxygen and hydrogen, oxygen, hydrogen. Now, these bonds are covalent bonds, but they're called polar covalent bonds because when you look at these atoms in here, hydrogens and oxygen is very electronegative. Okay, which means that it's greedy with those electrons. It can't completely strip them away from hydrogen. It can't do that. But it's going to make it so that those electrons are closer to oxygen than they are to hydrogen. So these guys are just going to sit closer to the oxygen and further away from the hydrogen. And same with these guys. They're going to orbit closer to the oxygen, further away from this. So now when you look at the whole molecule, you start to get not a true charge. A true charge is when you get rid of electrons or gain electrons, like ions do. That's not what's happening here, but you get what are called dipole charges, these slight charges. So because electrons are negatively charged and the electrons are sitting closer to oxygen, you get this slight negative charge on that side of the molecule. And then because the electrons are further away from this hydrogen, you get this slightly positive charge down there. And that little swirly thing's just a dipole, okay? And then same thing over here. These two, because they're closer to oxygen, put a slight negative charge up there, and they're further away here, so you get a slight positive charge. Now, that's all well and good, The issue is when you start having multiple waters together, they will start to interact with one another in very predictable ways. So if you look at, if you put a little drop of water here, it's gonna beat up, right? It'll form like a little dome. If you take a little puddle of water, you might see insects walking across it. That's all because of surface tension, okay? That's surface tension. So essentially what happens is, if I put another water here, it's gonna orient itself like this. So the slight negative on this molecule is gonna be by the slight positive on this one. And that interaction right there, that's hydrogen bonding right there. That's a hydrogen bond. They're really weak, but they're super important. They're important for how proteins fold. They're important for the fact that water does this. So when you look at the surface of a bunch of water, the surface, the water is like holding hands, and it makes a nice surface tension, a tension on the surface. Now back to these guys. When you make the volume smaller in the lungs, the water molecules will be attracted to one another in this alveoli, and they will want to interact with one another. And as they start to interact, it pulls the edges inward. So this surface tension, or the hydrogen bonding between water molecules in the alveoli, causes alveolar volume to drop, which is good. We need it to drop so that the alveolar pressure will go up and we can exhale, right? We need that to happen. The problem is, if this is all that we had right here, because these are such fragile little structures, and that surface tension actually is pretty strong for such a fragile little structure, they would recoil so much that they wouldn't pop back open. They would essentially collapse and stay recoiled. So we need this to happen. We need surface tension to happen, but we need it to not be quite that strong. It's too strong. If that's all that we had, those guys would not expand when the lungs increase their volume. When the lungs increase the volume, these guys would not pop open because that's too strong. So the way we get around that is at 7 months in utero, so as a fetus, 7 months as a fetus, the fetus starts to make what's called surfactant. Okay. Now, I'm gonna ask you this for sure in the test. It'll probably even be a short answer question, okay? So surfactant is made by cells that are embedded in here that we're not defining, okay? They're called type 2 pneumocytes. You don't need to know that. You can just say they're cells that are in the alveoli, okay? Make this surfactant. And it starts being made 7 months in utero, and it's made throughout your whole life. Surfactant is just lipoproteins. They're just proteins with fats attached to them. And those fats start to interfere with how water can interact with itself. It doesn't stop surface tension because we need that for volume to drop and pressure to, actually let's finish this. We need surface tension for the volume of the alveoli to drop so the alveolar pressure can rise and we can do expiration. We need that. But if that's all that we had, we would never be able to inhale because we couldn't get everything, the volume, the pressure low enough and the volume high enough. So these lipoproteins, the surfactant, what it does is it basically lines the alveoli And as that surfactant lines the alveoli, it decreases how strong that is. It doesn't stop it, it decreases its strength. Decreases its strength. So that when thoracic volume goes up, the alveoli can pop open. Okay? So this surfactant allows alveolar volume to be able to go up, which is going to allow alveolar pressure to drop, which is going to allow for inspiration. If you didn't make surface tension, so let's think about a preemie, right? A preemie that was born at 6 months. A preemie born at 6 months can't take a breath in on its own because it can't get its alveoli to pop open because it doesn't have surfactant. It can't overcome the strong surface tension. So what they do is they give it a treatment basically of surfactant so that then surface tension's not so strong, the alveoli can expand, volume goes up, pressure goes down, and then they can take a breath on their own. And eventually, as that baby develops, it will start making surfactant. Okay. So I'll ask you something about that, like what is surfactant? When is it made? If you don't have it, what's the problem? And you'd walk me through that if you didn't have it, you could not take a breath in, but you'd walk me through all this stuff.
Okay.
Okay.
Got it.
Okay. When you first see it, it's like, holy crap, right? It's a lot. But
Yeah.
as you start walking through it, it's a nice story, right? It will loop back on itself. You just have to start writing it out. And as you're doing it, just stop and say, what do I need? And ultimately, it's all about air only moves from high to low pressure and volume and pressure inversely related. You just walk your way through the whole thing,
Okay.
okay?
And then when the alveoli recoils,
Uh-huh.
is the H2O, are the interaction between those two stronger compared to how it is expanded?
It will still have enough surface tension to allow it to recoil. Yeah. So you still have all that, you're just decreasing quite the strength. It's still enough to recoil, but now it's not so strong to recoil to the point of collapse.
Okay.
Okay,
Thank you.
you are well done.
But yeah, it made a lot more sense now because I know in the video it was